Hello everyone, welcome to this series of lectures on the course Foundations of Mathematics. In this lecture, I will discuss Cantor's theorem. So before going on to the theorem, let's look at this. Supposing I have one set, a non-empty set consisting of single element, let's say E. Okay, I have a singleton set with me. So which are the subsets of this set? That is, which are the elements in the power set of this set? So empty set is a subset of every set. So empty set will come in the power set of this set, right? And I can have the set entire set X itself. That's the singleton set A. So the power set of the singleton set has two elements, namely the empty set and the singleton set A, right? Now I will define a function from X to the power set of X. Okay, so let f from X to power set of X, I want to find a function here from X to the power set of X. Now the question is it possible for me to find a onto function from X to the power set of X or not? Okay, so I have a function f from X to the power set of X. Can f be onto? This is the question. All right, so X has only one element, that's A. So this is X, and power set of X has two elements. One is the empty set and second element is the singleton A set, right? So I have a function now from X to power set of X, that's f. Can this map be onto? Now I have one point here A inside the set X. Okay, so I can map it to any one of them. Let's say I map it to the empty set. Okay, so let's say f of A is empty, this subset empty set of X. Then is there any pre-image for this second subset, that is singleton A inside the power set of X? Can you find a point here which is mapped to this? There is only one point in the set X. So if you try to map this point to this subset, that is singleton A inside the power set of X, then it will violate the definition of the function, because one point will have two different images. That's not allowed in a function, right? So that means this point now, singleton A, will not have any pre-image in the domain. That means this function f, which I have defined here from X to power set of X, cannot be onto, right? So this is an example of a set X which is a singleton set, and I can generalize this idea. Okay, if you take a set containing two elements A and B, there will be four elements in the power set of X. And again, this problem will come, you won't be able to define a onto map from X to power set of X. Alright, so we generalize this observation is Cantor's theorem. So it says if you have any non-empty set X, then there is no onto function from X to power set of X. Okay, so we will take an arbitrary function from X to power set of X and we will show that it is not onto. So let f from X to power set of X be a function, any arbitrary function. What we are claiming is this function f cannot be onto. Okay, our claim is f is not onto. That means I have to find one point in the codomain which does not have a pre-image, right? So if I do this, then I can say that the function f from X to power set of X is not onto. So let me take a point, some point in the set X. So let's say let small x belongs to capital X. then f of x will be there in the codomain, that's power set of x, right? But what are elements in the power set of x? They are subsets. So we are mapping points from x to subsets of x. Okay, remember that. So f of x is a point in power set of x. What does this mean? That is, it means that this f of x now, it's a subset of x because it is a point in power set of x. And power set of x contains all subsets of x, right? So f of x, this guy must be a subset of x because it's an element of power set of x, right? Now small x is an element in capital X and f of x is a subset of capital X. So there are two choices now. Then either this small x belongs to f of x, which is a subset of x, or x does not belong to f of x, right? Because I have the set x here and f of x is a subset of x, so it should be somewhere here. Now when I say x, small x is there in capital X, it could be either here or it could be here. Okay, one possibility is that it is here outside f of x. Second possibility is that it is here inside f of x. Okay, but exactly one of this will happen. Either x is there in f of x or x is not there in f of x, right? So what we will do is I will form a set B which will be a subset of x, okay, and I will collect all those points x in x such that x is not there in the subset f of x. So if I pick up any point in capital X, either it is there in f of x or it is not there in f of x. I will collect all those points from the set x which are not there in f of x. So that's a subset of x because I am collecting points from the set x itself, right? Now this B being a subset of capital X, it must be a member of the power set of x, right? Because power set of x contains all subsets of x. Then this B belongs to power set of x. That means we have found one point in the codomain of f, that's power set of x. Okay, because f is a function from x to power set of x. So B is a point here now in the codomain. What we will show is this point B inside power set of x, which is a subset of x, does not have any pre-image. Okay, and hence f will not be on. Okay, so to show that B does not have a pre-image under the function f, of course. Okay, so we will assume that this is not true and we will assume that this set B now has a pre-image. So let, if possible, there exists a point B in X such that f of B is equal to capital B. I am assuming that this point capital B in the power set of X is having a pre-image, namely small b. Then small b is a point in X, right? Now this point can be in B or it may not be in B. There are two possible cases because B is also a subset of X, right? So case 1 here will be when this point B is sitting inside the set B. If B is in capital B, what kind of points are there in capital B? All points which are not there in f of that point, right? So small b is there in capital B, this implies B is not there in f of B, right? But from here, f of b is nothing but capital B. So this implies b is not there in capital B. So I'm saying that b is there in capital B, b is not there in capital B. That's a contradiction, right? So the statement here, b is there in capital B and its negation both are true. That's not possible, right? So that's a contradiction. So b cannot come inside the set B. That's ruled out now. So the only possibility now for small b is that b is not there in capital B, right? So this capital B, it should be this way. Yeah. All right. So even here, this B is, yeah. So second possibility is that B is not there in capital B. But when do you say that a point is not there in the capital B in this set? If it is there in the image of that point, right? So this implies B is not there in capital B. That means B is there in f of B, right? But what is f of B? That's capital B. So this again means that B is there in capital B and B is not there in capital B. So that's a contradiction. So in both the cases, I'm getting a contradiction. So why we are getting this contradiction? Because we assume that the set capital B is having a pre-image. Okay, so therefore our assumption is false. Our assumption is false, and hence capital B does not have a pre-image. Okay, capital B does not have a pre-image in the set capital X, and therefore the function f, which was from x to power set of x, is not onto. So in general, I can say that there is no onto function from a set to its power set. Okay. Now a question for you is, can you define a 1-1 function from the set x to the power set of x? The answer is yes, and I want you all to define a function from x to power set of x which is 1-1. Okay, and using this Cantor's theorem, I can say that there is no bijection from any set capital X to power set of x, because you cannot find a onto function from x to power set of x. That's not possible. That means you cannot find a bijective function from x to power set of x. Okay, so this follows from Cantor's theorem, and I would like you all to think over this exercise and construct a function from x to power set of x which is 1-1. All right, so that's it for this session. These are my references. Thank you.